All right, folks, continuing our journey through chapter 2, looking at a lot of limits. Now we're going to look at limits at infinity. This is section 2.5. And we're going to introduce it by looking at the graph of the function f of x equals x plus 1 over x. So there's the graph of the function f of x equals x plus 1 over x. So in this section, when we say we're going to analyze limits at infinity, what we're going to do is we're going to let the independent variable, so here it's x, head off to infinity or negative infinity. So in other words, we're going to let the independent variable x increase without bound, and we're going to also look at letting it decrease without bound. Now from the graph, I think we can determine a couple of limits right now. I mean, it looks like we have the limit as x approaches negative infinity. So let's see, my x's are going to head off to negative infinity. My x's are heading off to the federal debt and beyond. It looks like those y values would be getting close to, well, this red dashed line. Going to be getting close to 1. If we let x head off to positive infinity, so x is heading off to positive infinity, the values of x are increasing without bound. It looks like those y values are getting close to the red dashed line, which is positive 1. Now that red dashed line, you're probably saying to yourself, hey, that's a horizontal asymptote. And you're correct. Notice how the horizontal asymptote really aided our analysis and helped us determine these limits. So let's check out another example here. You should get this in your notes for sure. The graph of the function f of x equals 2x squared over x squared plus 3. I have the graph of that function over here to the right. So let's determine the limit as x approaches infinity of 2x squared over x squared plus 3, and the limit as x heads to negative infinity of 2x squared over x squared plus 3. I mean, you're probably looking and you're saying, hey, y equals 2. That's the horizontal asymptote. So that graph tells us that both of these limits are 2, and you would be correct. Both limits are 2. But let's head off to the chalkboard. I want to kind of discuss a little bit more precise mathematics and establishing that these limits are in fact 2. So here I go, heading off to the chalkboard. All right, folks, this example we just saw in the slide, I had the graph of the function presented, and we were able to graphically determine that the limit as x approaches infinity of 2x squared over x squared plus 3 was 2, and the limit as x approaches negative infinity of 2x squared over x squared plus 3 equals 2. And I said we were going to head off to the chalkboard, and I was going to highlight some different ways to look at it. So the first thing I'm going to do is talk about number sense. So folks, 2x squared over x squared plus 3. For really, really, really large values of x, so as x is heading to infinity, so I'm talking really large values of x, like Bill Gates' bank account. If you let something really large come in for x, this plus 3 doesn't have much of an effect at all. I mean, do you think if I were to put $3 into Bill Gates' bank account, he would even notice it? So for really, really large values of x, this is really, really close to 2x squared over x squared. Likewise, for really, really large negative numbers, as we're heading off to negative infinity, say the federal debt. If you were to put a large number like the federal debt in for x, this plus 3 has a minuscule effect. So for large negative numbers, 2x squared over x squared plus 3 is really, really close to 2x squared over x squared. I mean, you think of today, I transferred $3 from my checking account towards the federal debt, paying down the federal debt, it wouldn't be noticed. So that's why I have the wavy equal signs here, because it's really, really close to this. So this is really, really close to 2x squared over x squared. Now I can introduce the hardcore equal sign, because x squareds cancel out, and we have 2. So this tells me that the limit as x goes to infinity of 2x squared over x squared plus 3 should be 2. And the limit as x goes to negative infinity of 2x squared over x squared plus 3 should be 2. And the graph supported that. Can't stress enough this kind of number sense, how it's really going to pay off throughout calculus, especially in calculus 2 when we look at infinite sequences and infinite series. Okay, now let's talk about an algebraic way of doing it. And this algebraic way that I'm going to discuss here, it doesn't matter if x is approaching infinity or if x is approaching negative infinity. It would be exactly the same process. So let me write it down. The limit as x approaches infinity of 2x squared over x squared plus 3. And again, this is going to work if this were a negative infinity. So the key to the algebra is you look at the numerator, you look at the denominator. I mean, they're polynomials. Determine the largest degree of the numerator and the denominator. Well, the degree of the numerator is 2. The degree of the denominator is 2. So the largest degree is 2. So the algebra is divide everything in the numerator and everything in the denominator by x squared. That gives us the limit as x approaches infinity. Well, 2x squared divided by x squared is 2. In the denominator, x squared divided by x squared is 1. 3 divided by x squared is, well, 3 over x squared. And then as x goes to infinity, well, the limit as x goes to infinity of 2 is 2. The limit as x goes to infinity of 1 is 1. And the limit as x goes to infinity of 3 over x squared, 3 divided by an incredibly large number, is 0. And we get the limit to be 2. So let's head back to the slides and see what's coming up. All right, folks, just to reiterate at the chalkboard, we worked through what I called like a number sense talk. That's going to serve you well as you go forward in calculus, especially in calculus 2 when we look at infinite sequences and infinite series. It's not a hardcore, valid, mathematically precise way of doing something, but it really gives us a great idea of what's happening. And then we saw the really precise way, which was some algebra in order to determine those two limits. But let's tighten things up just a little bit. Look at this definition. The definition says the line y equals L is a horizontal asymptote of the graph of f of x if the limit as x approaches infinity of f of x is L, or the limit as x approaches negative infinity of f of x equals L. Well, folks, just like we saw in the prior section, we can turn things around and we can use our knowledge of an asymptote to tell us a limit. It's the same thing here. We're going to use our knowledge of how to find a horizontal asymptote. And if we know where there's a horizontal asymptote, then it tells us these limits. Before we look at that, though, I wanted to introduce a quick theorem. So in this theorem, R is a positive rational number. A is any real number. The limit as x goes to infinity of a over x to the r equals 0. So a is any number you can think of. A over x to the r, as x heads to infinity, that limit is 0. And furthermore, if x to the r happens to be defined for negative values of x, then the limit as x goes to negative infinity of a over r equals 0. You know, there's a theorem on page 75, theorem 2.6. I'm just telling you, check out that theorem. It's an okay theorem to look at. But let's look at an example and trying to find some limits. So 2 parts to this example. Part A, we're going to find the limit as x goes to infinity of 2 plus 3 over x to the 4th. And in part B, we'll find the limit as x goes to infinity of 3 plus cosine x over square root x. So you know the drill. Get this written in your notes because I am heading off to the chalkboard to work through these. All right, this example, we're asked to determine a couple of limits. So in part A, determine the limit as x approaches infinity of 2 plus 3 over x to the 4th. So let's start off by using one of those old limit theorem laws, that the limit of a sum can be rewritten as the sum of the limit. The limit of a constant, doesn't matter what we're approaching, the limit of a constant is that constant. And then the theorem that we just saw, the limit as x approaches infinity of 3 over x to the 4th, so that theorem was like an a over x to the r, we know that this limit here is 0. So for part A, we get the limit to be 2. That's all there is to it. Part B. Well, let's start off by using an old limit law. The limit as x approaches infinity of 3 plus the limit as x approaches infinity of cosine x over square root x. Well, we know the limit as x approaches infinity of 3. The limit of a constant is a constant, so this limit is going to be 3. This here, the limit as x approaches infinity of cosine x over square root x. That's going to take a little bit more analysis. So, you know what, I'm going to come over here to the side. I'm going to come over here to this area, so I have to erase this, to do a little bit of work in trying to analyze this limit as x approaches infinity of cosine x over the square root of x. Okay, so in trying to analyze that piece, I know, you know, we know that cosine x is trapped between -1 and 1. We know for all values of x, cosine's between -1 and 1. As long as x is not 0, and x is heading off to infinity, so I would be well past 0, I can divide each piece of that compound inequality by the square root of x. I know that the limit as x heads off to infinity of -1 over square root x. That was that theorem we just looked at. The a over x to the r. R is a real number. I mean, square root of x can be rewritten as x to the 1/2. I know this limit is 0. I know the limit as x heads off to infinity of 1 over square root x is also 0. So thanks to the squeeze theorem, I told you it would keep popping up, the squeeze theorem tells us that the limit as x approaches infinity, cosine x over square root x, is also 0, and that's thanks to the squeeze theorem. So to finish off part B, we know the limit of a constant is that constant. We have just figured out that the limit as x approaches infinity of cosine x over square root x is 0, thanks to the squeeze theorem. So for part B, we get the limit to be 3. I'd like you to practice a couple of these. So in your book, do exercise 18 and exercise 26. So section 2.5 exercises, pause the video, do numbers 18 and 26. After you've done them, restart the video, and I'll be here at the board working through the solutions. Okay, folks, number 18, you're asked to find the limit as t approaches infinity of 5t squared plus t sine t, all of that over t squared. I would actually start by using the fact that the denominator is a single term, so I could split this into two fractions. It's like the meaning of a common denominator, to get 5t squared over t squared, which would simplify down to 5, plus t sine t over t squared. That would simplify down to sine t over t. Then we have the limit as t heads off to infinity of 5, plus the limit as t heads off to infinity, sine t over t. We know this limit is 5. So now what about this limit right here? The limit as t goes to infinity of sine t over t. Well, hopefully you use the squeeze theorem there. Hopefully, so I'll do it like a quick little aside here. Negative 1 is less than or equal to sine t is less than or equal to 1. So negative 1 over t is less than or equal to sine t over t is less than or equal to 1 over t. Just divide each piece by t. The limit as t goes to infinity of negative 1 over t is 0. And the limit as t goes to infinity of 1 over t is also 0. So thanks to the squeeze theorem, the limit as t goes to infinity of sine t over t, it too is 0. So 5 plus 0 gives you the limit to be 5. Number 26. So the limit as x goes to infinity of 9x cubed plus x squared minus 5 all over 3x to the fourth plus 4x squared. So the degree of the numerator is 3. The degree of the denominator is 4. So 4 is the larger degree. So I would divide everything in the numerator by x to the fourth and everything in the denominator by x to the fourth to give me the limit as x approaches infinity. Okay, so 9x cubed divided by x to the fourth will give me a 9 over x. X squared divided by x to the fourth is 1 over x squared. 5 divided by x to the fourth, well, that just gives me 5 over x to the fourth. In the denominator, 3x to the fourth divided by x to the fourth is 3. 4x squared divided by x to the fourth gives me a 4 over x squared. And then, I'm not going to rewrite this using the quotient law of limits, and then the sum and addition. I'm just going to kind of verbalize each one. The limit as x goes to infinity of 9 over x. That's 0. The limit as x goes to infinity of 1 over x squared. That's 0. The limit as x goes to infinity of 5 over x to the fourth. That's 0. The limit as x goes to infinity of 3. Well, the limit of a constant is the constant, so it's 3. And the limit as x goes to infinity of 4 over x squared is 0. So you get 0 plus 0 minus 0 over 3. You get the limit to be 0. All right, hopefully you got both of those. Let's head back to the slides and see what's coming up. All right, folks, that last example and the two exercises I asked you to practice utilize some old properties of, limits, some old limit properties, limit theorems, if you will. We also saw the squeeze theorem. As I told you, the squeeze theorem is going to continually pop up throughout the calc sequence. And we saw how to use our little, algebraic technique to find some limits. So I wanted to take just a little bit of time to review something else that you learned in college algebra. In college algebra, when it came to polynomial functions, you did learn about the end behavior of polynomial functions. And the end behavior depended on whether or not the degree of the polynomial was even or if the degree of the polynomial was odd. So here I'm going to say, let's look at the end behavior of polynomial functions that are even degree polynomials. So if you have an even degree polynomial and the leading coefficient is positive, that's like a generic looking graph. I don't really care what's happening in this area here for these small values of x. It's the end behavior as x heads to infinity or as x heads to negative infinity. Notice both ends are shooting up. If you have an even degree polynomial and a negative leading coefficient, the end behavior as x goes to infinity or as x goes to negative infinity, both ends of the graph are shooting down. You probably remember all this from college algebra, and that's good. So let's look at the end behavior of polynomial functions that are odd degree polynomials. So if you have an odd degree polynomial and a positive leading coefficient, there's a generic graph. Keep in mind, I don't care what's happening for small values of x. It says x heads to infinity or as x heads to negative infinity. Notice as x heads to positive infinity, this end is shooting upwards. When x goes to negative infinity, this end is shooting downwards. If you have an odd degree polynomial and a negative leading coefficient, well, as x heads to infinity, the graph is shooting, as x heads to infinity, the graph is shooting down. As x heads to negative infinity, the graph is shooting up. So it's the end behavior of polynomials that can tell us limits. So let's just practice something real quick. Determine the following limits. In part A, the limit as x goes to infinity, 3x to the 7th plus 2x squared. Part B, the limit as x goes to infinity of negative 3x to the 7th plus 2x squared. Part C, the limit as x goes to negative infinity of 3x to the 7th plus 2x squared. Part D, the limit as x goes to negative infinity, negative 3x to the 7th plus 2x squared. And then D, limit as x goes to infinity of 3x to the 6th plus 2x squared. And in F, the limit as x heads to negative infinity of 3x to the 6th plus 2x squared. So folks, get this written down. I'm going to head off to the chalkboard. We're going to quickly crank through this example. We're going to rely on what we just reviewed from college algebra, the end behavior of polynomial functions. So here I go to the chalkboard. Hey folks, this example is just kind of really, if we remember something from college algebra, the end behavior of polynomial functions, these limits can be knocked out very, very quickly. So in part A, you have a 3x to the 7th plus 2x squared. That's a polynomial function. The degree is 7. That's an odd number. The leading coefficient is positive. So because the leading coefficient is positive, and it's an odd degree polynomial, we know the end behavior of the graph. We know that end shooting down, this end is shooting up. Who knows what's happening for the small values of x? It doesn't matter. But it tells us that this limit, as x goes to infinity, it tells us that this limit is infinity. In fact, while I'm here, let's do part C. 3x to the 7th plus 2x squared, the limit as x goes to negative infinity. It's negative infinity. So just knowing the end behavior, we get these limits very quickly. Okay, in part B, the function was negative 3x to the 7th plus 2x squared. It's an odd degree polynomial. The leading coefficient is negative. Because of that, we know that end's shooting up, that end's shooting down. We don't know what's happening for the small values of x. It doesn't matter. We're talking about the end behavior. So the limit as x goes to infinity. Well, that end's shooting down. So that would be negative infinity. And while we're here, let's do part D. The limit as x goes to negative infinity. That end's shooting up. So the limit's infinity. Part E is the limit as x goes to infinity of 3x to the 6th plus 2x squared. This is an even degree polynomial. It's an even degree polynomial. The leading coefficient is positive. That means both ends are shooting up. Who knows what's happening for the small values of x? Who cares? We're talking the end behavior. But it tells us that this limit, because that end shooting up, is infinity. And well, as x goes to negative infinity, it's the same function. We get that limit to be infinity. So that's all there is to it. So just knowing that the end behavior of polynomial functions, which is determined by the degree, whether it's even or odd, and the leading coefficient, whether or not it's positive or negative, these limits can be knocked out very quickly. So let's head back to the slides and see what's next. All right, folks, might as well review something else from college algebra that's going to be beneficial for us, and it's the end behavior for rational functions. So if you have a rational function, p of x over q of x, remember p and q are polynomial functions. So I'm going to say the degree of the numerator, p. I'm going to say the degree is m. The degree of q, the denominator, is n. And then I'm just saying, hey, the leading coefficient of the numerator, p, is a. And the leading coefficient of q, the denominator, is b. Knowing that information, if m is less than n, so if the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is the horizontal asymptote of the graph of f. And as a result, we know the horizontal asymptote. We know the limit as x heads to infinity, or the limit as x heads to negative infinity of the function would be 0. We know the horizontal asymptote. We know limits. Now, if m is equal to n, so if the degree of the numerator is equal to the degree of the denominator, then the line y equals a over b. Remember, a is the leading coefficient of the numerator, b is the leading coefficient of the denominator. Well, that line would be the horizontal asymptote for the graph of f. And as a result, if we know the horizontal asymptote, we know limits. We know that the limit is as x heads to infinity or negative infinity of f of x would be a over b. So the only situation that's left is, what if the degree of the numerator is larger than the degree of the denominator? Well, when that happens, there is no horizontal asymptote for the graph of f of x. And the limit as x heads off to positive or negative infinity of f of x, well, it's going to be positive or negative infinity. So you might remember that from college algebra. But you know what? Let's look at an example here. Let's determine the following limits. So we get these written down in your notes. Parts B and C are going to require an algebraic technique that I discussed earlier, in this section. And we're also going to have to remember a special definition from college algebra when we do parts B and C. So get this written in your notes, because I'm heading off the chalkboard to work through them. All right, folks, now we're learning a much more efficient manner to determine a limit as x approaches infinity or negative infinity, especially if we have a rational function. Remember, a rational function is a polynomial over a polynomial, such as part A. The limit as x goes to infinity of 2x cubed minus 4x squared plus 7 over 7x cubed plus 5x minus 3. That's a rational function. So we can use old ideas like the horizontal asymptote and how the horizontal asymptote tells us this limit. So I look at the degree of the numerator, it's 3. The degree of the denominator is 3. So when the degree of the numerator is equal to the degree of the denominator, if I were to graph this, the horizontal asymptote is the line y equals leading coefficient of numerator over the leading coefficient of the denominator. Because I know the equation of the horizontal asymptote, that tells me that the limit as x goes to infinity of 2x cubed minus 4x squared plus 7 over 7x cubed plus 5x minus 3, it tells me that limit is 2/7. Now part B, well, I don't have a rational function. I don't have a polynomial over a polynomial, so it's not a rational function. So I'm going to use that old algebraic technique of dividing the numerator and denominator by something. And I'm going to divide the numerator and denominator by x. But watch, because there's a little subtlety here. I'm going to divide the numerator by x. I'm going to divide the denominator by x, but the version of x I'm going to use is the square root of x squared. Okay, so now I need to erase part A because there's something that we need to discuss. This too is something that keeps popping up throughout mathematics, and you have to have a handle on this definition. The square root of x squared, it does not equal x. The square root of x squared equals the absolute value of x. And absolute value of x is defined to be x, well, if x is greater than or equal to 0, the opposite of x if x is less than 0. This has got to be remembered. The square root of x squared is the absolute value of x. But in part B, x is heading to infinity. Because x is heading to infinity, we're talking positive numbers. Positive numbers. The square root of x squared is x. So I'm dividing the numerator by x, and I'm going to divide the denominator by x, but I'm disguising the x as square root of x squared. So that gives me, well, 2x divided by x is 2. So the denominator, well, I'd have the square root of x squared plus 2 divided by the square root of x squared. Well, there's an old property of radicals that says the square root of x squared plus 2 over the square root of x squared. I can make that the square root of x squared plus 2 over x squared. So that there's an old property of radicals that looks something like this. It looks like this. Square root of a over b, you can rewrite it as square root of a over the square root of b. I'm using that old rule of radicals, but I'm actually going in this direction. And I'm doing that because now under the radical, I can do a little bit of simplifying. X squared over x squared. Well, x squared over x squared is 1 plus 2 over x squared. Now as x heads off to infinity, I'm going to do this one at a time. The limit as x goes to infinity of 2 is 2. the limit as x goes to infinity of 1 is 1. The limit as x goes to infinity of 2 over x squared is 0. 1 plus 0 is 1. Square root of 1 is 1. 2 divided by 1 is 2. So part B, the limit is 2. Now notice in part C. It's the exact same function as in part B, except there it's the limit as x goes to negative infinity. I'm starting it the same way. I'm going to divide numerator and denominator by x, but I'm going to disguise that x in the denominator like I did here in part B. I disguised it as a square root so I could take advantage of this old property of radicals. I'm going to disguise that x as the opposite of the square root of x squared. So now why do I have to do that? Folks, in part C, x is heading off to negative infinity. X is a negative number. Because x is a negative number, the square root of x squared, is the opposite of x. X is negative. So the square root of x squared is the opposite of x. Well, if the square root of x squared is the opposite of x, that means the opposite of the square root of x squared is positive x. This is why it's so important to remember the definition of what square root of x squared is. Square root of x squared is the absolute value of x. And absolute value of x is defined as a piecewise defined function. So continuing on, let's see, I'd have, well, in the numerator, 2x divided by x, that's the 2. Denominator, we have the square root of x squared plus 2 over the opposite of the square root of x squared. And, well, everything looks similar to part B. Whoops, that's a negative infinity. I'm going to put that negative sign out front here. A radical over a radical, just like in part B, I can write that as square root of x squared plus 2 over x squared. Just like in part B, what's under the radical simplifies to 1 plus 2 over x squared. Just like in part B, I can actually start to evaluate the limits. So just like in part B, the limit as x goes to negative infinity of 2 is 2. The limit as x goes to negative infinity of 1 is 1. The limit as x goes to negative infinity of 2 over x squared is 0. So we get 2 over 1 plus 0 is 1. Square root of 1 is 1. The opposite of that is negative 1. So 2 divided by negative 1 is negative 2. So part C, the limit is negative 2. I can't say it enough, so let me mention it one more time. Folks, you have to remember this. It's going to keep popping up. Hey, I have a couple here I'd like you to practice. I don't know if either one of these are going to be as nasty as parts B and C, but in the exercises, right now, pause the video, do number 26 and number 40, and then you know the drill. After you've finished them, restart the video. I'll be here at the board working through them. All right, I asked you to do numbers 26 and number 40, and you probably were thinking, Bill, you've already asked us to do number 26. We've already determined what this limit is. Well, at that time when we did number 26, we had to divide numerator and denominator by something. But now that we know about horizontal asymptotes and how horizontal asymptotes can help us get these limits as x heads to infinity or negative infinity, I thought, look how much easier, look how much quicker it is to do now. So let's check it out. This is a rational function. The degree of the numerator is 3. The degree of the denominator is 4. When the degree of the numerator is less than the degree of the denominator, the graph has a horizontal asymptote at y equals 0, also known as the x-axis. Because we know that horizontal asymptote, we immediately know that this limit is 0. Done. In 40, you were given the function 12x to the 8th minus 3 over 3x to the 8th minus 2x to the 7th. And you were asked to find the limit as x approaches infinity of the function and the limit as x approaches negative infinity of the function. So I look at the function and I say, hey, this function's a rational function. It's a polynomial over a polynomial. The degree of the numerator is 8. The degree of the denominator is 8. When the degree of the numerator is equal to the degree of the denominator, the graph of the function has a horizontal asymptote at y equals leading coefficient of numerator over the leading coefficient of the denominator. And, well, we know 12 over 3 reduces to 4. Which immediately tells me, because I know the horizontal asymptote, I know this limit is 4, I know that limit is 4. And I'm done. So hopefully you're able to knock those two out pretty quickly. Let's head back to the slides. I think I have one more final quick comment, and it pertains specifically to the trig functions, sine and cosine. So let's head back to the slides and see what I have to say about those two trig functions. All right, before we continue, we just did, parts A, B, and C of that example, and I asked you to do numbers 26 and 40, but it's worth mentioning one more time. Please remember going forward, this is something that just keeps popping up regularly throughout the calculus sequence. That is, the square root of x squared is equal to the absolute value of x. And then you have to remember absolute value of x equals x. If x is greater than or equal to 0, absolute value of x equals the opposite of x if x is less than 0. So please remember the square root of x squared equals the absolute value of x. So here's my final note in this section. And this final note is kind of, based on something that, you never know when it's going to pop up. Trig functions. Cosine and sine. We know the graphs of cosine and sine. We know the graphs bounce back and forth between -1 and 1. The graphs produce what is called a sine wave. The graphs could also be said to oscillate between -1 and 1, kind of using language to match up with the phrase sine wave. That means these limits as x approach infinity or negative infinity of cosine x, and the limit as x approaches infinity or negative infinity of sine x, these limits are both said to oscillate. I mean, we know as x heads off to infinity or negative infinity, the graph, as I just said, it bounces or oscillates between 1 and -1. That means that those limits do not exist. The limit as x heads to infinity or negative infinity of cosine x does not exist. The limit as x heads to infinity or negative infinity of sine x does not exist. Neither one are you approaching a single number. There's no horizontal asymptote. Those limits do not exist. Well, folks, that's it for this section. That's it for section 2.5. So at this time, you are all set to do the exercises in section 2.5. So please do the exercises listed for section 2.5. Thanks for watching.